you define a linear transformation in this manner, and this is a linear transformation for this. Using the identity, I tried to establish an identity, and once I have this, so here, once I have this, I can say that V T star A of W, V T star A of W. So this is true for all V and W, V in V and W in W. So therefore you're going to say that this adjoint operator, which is defined in this manner, is the adjoint of the linear transformation. This actually, by the way, this will make sense. Anyway, so this is the first example of the linear transformation. So for a linear transformation, you can define the adjoint in this manner. For a given matrix, adjoint is really simply the conjugate of it, or adjoint matrix. Okay. Let's move to the next example. The next example goes like this. Pretty simple example. So let's take field to be the set of complex numbers, and let's take in the previous example as m and as one dimension, and let's take A to be a simple one by one scalar actually. So this is now a scalar simple. Then TA is going to be a linear transformation from C to C. Okay, and the definition of TA of V, where V is a complex number, is going to be simply AZ. Okay, it's going to be AZ for all Z in the set of complex number. The question, with all these calculations, what would be the T star of A operated onto Z? Okay, so the T star of A operated onto Z is going to be the conjugate of A times Z. So this is the adjoint operator of the scaling operator actually. So you have Z and you scaled it by, for example, the scalar A. I mean, the scaling would make sense if the A is the real number, but okay. So if you have such kind of a linear expression, its adjoint is basically this. Okay. What is another example? Let's do another example, a bit more non-trivial example. By the way, this example is a particular case of this. Okay, this example is a particular case of this. Now, the next example is that let's take V and W to be the space of inner product space of all polynomials, okay, with inner product. The inner product on V and W both is same, and that is like that if I have two polynomials f and g, then the inner product is L2 inner product, and that goes like that you integrate, say, f of x times g of x over the interval, say, 0 to 1. Okay, the polynomials on 0 to 1 with the inner product defined in this manner. So this is the inner product on V and W both. Okay. So in the next example, I'm taking both inner product spaces to be the space of all polynomials with the domain 0 to 1, and the inner product on V and W both is the L2 inner product, that okay, simply multiply the polynomials and integrate over 0 to 1. And I would like to define an operator for which I would like to have, the adjoint action. So I would like to define adjoint. So here's the thing. let us fix a polynomial P from space of the polynomial. Okay, so P is any degree polynomial, and corresponding to P, let me define a polynomial TP. Okay, so the P is a polynomial corresponding to this polynomial, and I am defining it from space of polynomial to the space of polynomial as that when Tp operates onto a polynomial f, what it gives is the product of the polynomials p and g. In other words, I'm getting p of x times g of x. Okay, so I'm getting p of x times g of x, where the p of x and g of x could be the complex numbers actually, because the both of the so in other words, these are the complex valued polynomials actually. So the p of x is a complex valued polynomial, and the g of x is also a complex valued polynomial. So this p of x is, sorry, I shouldn't write g of x, but f of x. Yes. Okay, f of x. So in other words, multiplying every polynomial of the polynomial space with, say, some polynomial p of x gives you this linear transformation Tp. And what I would like to do, I would like to try to find the adjoint of this polynomial actually. So here's the thing. So let's calculate Tp of f and its inner product with g, and I want to rewrite as something f something operated onto g. So if I can find that something, my that something is going to be Tp star. So the trick to find really the inner product, the adjoint, is to take this inner product and try to turn it into this kind of inner product. Whatever comes here is going to be the adjoint of the operator actually. Okay, so this is what I would like to do. So let's calculate, say, Tp operated onto f, g. So by definition, this is going to be 0 to 1. Tp of f is p of x, f of x, p of x, f of x times g of x bar conjugate dx. I think I must put a conjugate here. F of x times the conjugate of the g of x. Okay. Now what can be done? Now this can be done that if I keep this f of x aside and I write the both expression as p of x times g of x, but I put a conjugate on it. Then I need to put a conjugate here times dx. Because what would be the conjugate of the conjugate p of x d of x? So the conjugate of the conjugate is going to be p of x times the conjugate of g of x. Okay? And hence I can rewrite this again as inner product. So I can say that this is equal to the inner product of f with p bar multiplied by g. With p bar multiplied by g. So let me define, say, a phi from t star from again p to p by that when t star operates onto g, it gives me p bar multiplied by g. So we can show that this is also a linear transformation. So with this definition, this will become what? F and t star g. Okay? And hence we have identity that maybe if you wish, you can put a p here. You can put a p here as well. Doesn't matter. So the Tp f g is equal to f Tp star g. So for this operator, the adjoint operator is what? Simply take the conjugate of p of x and multiply with the input. Okay, so this is really the required adjoint operator. Okay, so I hope that it makes sense that why this tp star is adjoint of tp of s. So what actually we have to do, just try to write this as this, and as I said, whatever is going to come here is going to be the adjoint of the tp star. Okay. Let me put a definition. Let me put a definition. Little definition. Little definition. So let T is a linear transformation from inner product space V to V, and T star, which is going to be another map from V to V, be its adjoint. Adjoint. Okay. So if the adjoint, if you compute the adjoint of a linear transformation, okay, if you compute the adjoint of a linear transformation, and it turns out the adjoint is equal to the linear transformation, then you're going to say that then the T is self-adjoint operator. Self-adjoint operator. Okay. So it's evident from what you call the name that an operator is self-adjoint if it is itself the adjoint of if the operator itself is the adjoint actually. So you call such linear transformation as the adjoint linear transformation. And once you have such a linear transformation, you can also define what you call the adjoint matrix, self-adjoint matrix, or what you call the Hermitian matrix. Okay. Self-adjoint matrix or the Hermitian matrix. So if further in the definition, if A is in a square matrix n to n, okay, should be in a square. The self-adjointness does not make sense for the space where you have a different dimension actually. So if A is an square matrix, then A then A is called adjoint, either adjoint, or a better word for it is Hermitian. Okay, the better word for it is Hermitian if A star is equal to A. Okay, so if the A star equal to A, if the conjugate of the matrix is equal to itself, or the adjoint of the matrix is equal to itself, you're going to call such matrix as Hermitian actually. Okay. So another way to say or know that what is the adjoint of a linear transformation is that take the linear transformation and construct, for example, if you are in finite dimensional case, obviously, take the linear transformation, construct its matrix, and construct its corresponding matrix representation. And if that matrix is Hermitian, okay, if that matrix is Hermitian, then you're going to say that your linear transformation is self-adjoint actually. Okay, then linear transformation is self-adjoint. So that would be another way to say it actually. Okay. So for Hermitian matrices, for self-adjoint matrices, we don't use the self-adjoint matrices, we use the word Hermitian. Okay. For example, in this, I'm going to say, so in this example, I can say that this Tp of f equal to p of x times f of x, this operator, this is a self-adjoint operator. Self-adjoint operator if and only if what happens? Now, when this guy would be equal to this guy, this would be equal if the p bar of x is equal to p of x. Okay. Say for example, you also applied this on f, then you're gonna obviously have an f of x here. Okay. Then when this Tp star is equal to Tp, so when the adjoint of T is equal to itself, the both are going to be equal because everything is equal if and only if, in other words, this would be equal to if the p of x is equal to the conjugate of the p of x. And under what condition a complex number is equal to its conjugate? The conjugate of a number is equal to itself if it is purely real. So you can say that this operator is self-adjoint if and only if P is a real polynomial. It's a polynomial with the real coefficient. It's a real polynomial. Okay, so if the P is real, then Tp is a self-adjoint, what do you call, operator? You have to, yeah. By the way, one simple remark is also this, that since, here's a little remark, and let me write here. So I know that T is self-adjoint if and only if T is equal to T star. But this is also true if and only if, say, TV W is equal to what? V T star W, but the T star W is equal to T, so TW. So if the TVW is equal to VTW for all, you know, V in V and W in W, you're going to call your operator T as a self-adjoint operator actually. So this is another criterion actually of an operator to be self-adjoint, that compute the TVW, okay. By the way, this W is not going to be W, but it's going to be V now, okay, because the transformation is from V to V, okay. So if the inner product of TVW is equal to VTW for all V and W in V, your operator is a self-adjoint operator actually. So just verify this and you're going to have your operator is self-adjoint operator, okay. This is also the case actually. All right. Let's do one example. So what I'm going to do next is one of the final thing that so what I'm going to do next, I'm going to do one example. So let's do one example. But this example is an example for which we show that not every single operator has an adjoint actually. Okay? So there are operators which do not have any adjoint. There are linear transformations which do not have any adjoint actually. Okay? So here's an example. Let's take V and W as previously, that it's the space of the polynomials on the interval 0 to 1. Okay? And define a linear transformation T that is equal to the derivative of the derivative of it actually. So in other words, this is equal to d f of x by dx. Okay? So the differentiation operator. So obviously we know the differentiation is a linear transformation, so I defined my operator in this manner. And if the differentiation is a linear operator, okay, we know why differentiation is a linear operator, because differentiation preserves the addition and scalar multiplication. So it has both properties, that the sum of the derivative is equal to the derivative of the sum, and derivative of a number multiplied by a function is equal to number multiplied by the function of the derivative. So you know that why differentiation is a linear transformation. Now, what I would like to do, I would like to try to find an adjoint for it. And my claim is T has no adjoint. T has no adjoint. Okay? T has no adjoint. So how I'm going to do, I'm going to prove this by contradiction. So I'm going to say suppose contrary that T has an adjoint actually. Has adjoint T star. Okay? And I'm going to show that you have a trouble. You have a trouble. Okay? Now let's take g of t to be a constant polynomial. So it's a polynomial that is equal to 1. And I know that T star is going to be a map from P to P. So the T star of the constant polynomial G is going to be a polynomial actually. So I don't know what polynomial it is going to be because I don't know the definition of the T star. So let's call that polynomial H actually. So let H be the, what do you call, be the output of T star of G. Okay. Now from the fundamental theorem of calculus, let's calculate say TF G, the inner product of TF with G. So by definition, this is going to be 0 to 1. The TF is the derivative, f prime of x, and G is 1 times dx. So you get what? 0 to 1, f prime of x and dx. So by fundamental theorem of calculus, this would be equal to the f of x evaluated at 0 and 1. In other words, it's going to be f of 1 minus f of 0. This is what is going to be the other side. So what I would like to do, I would like to calculate now the other side, f t star g. Okay, and we will see. So if t is really an adjoint actually, then this must be true. T star f tf g should be equal to TFG should be equal to f t star g for all f and g from the space of the polynomial. So if you can show, or if we can show that there is one f and one g for which this does not holds, then T star is not adjoint. But since T star is adjoint, this must hold. But this will lead us to a contradiction actually, because I'm going to choose f and g for which this does not hold. And hence that would be a contradiction to the adjointness actually. Okay. So what we calculated f of 1 minus f of 0 to be equal to tfg. Okay, so this is what that we did. But since T star is adjoint of G, this would be same as f T star G. But f T star G, I have given it a name h actually, so it's going to be f of t. Okay, so it's going to be f of t g bar of f of t and h of t. H of t. Okay. And what would be this inner product now if I calculate it explicitly? So it's going to be the integral from 0 to 1 f of t or f of x, doesn't matter, g of h of t bar and dx. So this is what it is going to be. Okay. And now see the background. So in other words, f of 1 minus f of 0 is equal to this. Now consider this particular f of t. Consider this particular f of t that is, because, by the way, this identity that we have proved, in this f is abstract actually, it's general, it's not specific. I can choose any f I would like and this would always hold actually, by definition. So let's now choose a particular f and see what happens. So let's choose f of t to be t square t minus 1 square and h of t. Okay, and times h of t, and h of t is the same as this. So if I substitute that here, so I'm going to get what? F of 1 minus f of 0. F of 1 minus f of 0, this is going to be equal to 0 to 1. T square, t minus 1 square, h of t, h bar of t and dt. Okay, this is what that you're going to get. So what would be h of t times h bar of t? So this is going to be the conjugate square, t square, t minus 1 square and the conjugate of h of t square dt. So this is what that you're going to get. Okay. And now what does this shows? What does this shows? So this is equal to f of 1 minus f of 0. By the way, if my f of t is this, what would be f of 1? So it's going to be 1 square, 1 minus 1 square, 0. So this is going to be equal to 0. What would be f of 0? So f of 0 is also going to be 0. So this guy is equal to 0. So f of 1 is 0, f of 0 is 0, so this is equal to 0. Now I have an integral of a non-negative function. Okay? A non-negative function. Why? Because these all are squares and all of these are equal to 0.